Hi everyone, this is HLS final project team, and we were working on JPEG compression accelerator. To start with, we introduced the lossy JPEG compression algorithm. The algorithm works by reducing the resolution of high-frequency pixel data, and the algorithm can be divided into 5 stages. First is to convert the RGB image into white CBCR color space, and subsample the CB and CR channels into 2x2 blocks, and apply discrete cosine transformation to 8x8 blocks of pixels to get frequency contents, and quantize 8x8 blocks of pixels to filter out the high frequency data. And finally, use Huffman coding to optimally store the processed data.
Huffman coding is a method of losslessly compressing data. It works by calculating variable length codes based on a binary choice tree that is balanced based on the number of instances of each of the codes below the node. And this results in lossless image compression or lossless compression, but you have to store the data that is the tree data to decode the lossless compressed data.
As the baseline design, we implemented 5 functions according to the 5 steps of getting a JPEG image. We use a rows buffer to string the image data between each 2 modules to reduce the VRAM utilization. First, we string our image data in form of packed RGB into the FPGA, and the RGB to YCBCR module would convert the image data into YCBCR arrays. Second, we apply subsampling on the CBCR channels since our human eyes are less sensitive to these 2 channels. And then the DCT module utilizes a metric-to-metric multiplication to get each channel's frequency contents and quantize each channel with a quantization field table. So far, we use the FPGA to complete all the pre-processing of the image data for the Huffman coding. Because it is hard to implement a tree structure on FPGA, so we just put the Huffman coding part on CPU, and then we could get our final compressed image plus the decode tree.
To optimize the FPGA design, we use data flow to have multiple sets of row buffer blocks in flight at the same time. Then we optimize the DCT because this was the major latency source in this project. We optimized it by swapping from single value multiply accumulation steps to multiply accumulation steps for a full row of partitions buffer in a partitioned row buffer. This allowed us to sidestep the need for a massive adder tree when we pipelined the DCT matrix multiply. And then we've merged the DCT with the quantization step since the data flow optimization allowed for a no performance hit while reducing the LUT and VRAM utilization because the intermediate data type between the intermediate fixed point data type between the DCT and quantization step was very large. The fixed point data types were still pretty large, like 16 to 20 bits. However, going with fewer bits resulted in significantly worse noise that was visible to the human eye.
For the testing part, we use 5 640 by 480 PNG images to evaluate our implementation. And here is our evaluation result. Our evaluation method is to compare the quantization output from the FPGA with the reference the MATLAB output. We count the number of correct pixels and calculate the average squared distance between them. It could be shown that all the output accuracy is around 95%, and the value of the baseline and optimization are similar, which means our optimization didn't decrease the accuracy. The distance values vary from images to image, but there is not much difference between the baseline and the optimization. Therefore, for both the baseline and optimization, our algorithm implementations are functional correct.
The method of calculating compression was to actually not to actually compute the bit stream output of the Huffman encoding, but to estimate the size by calculating the number of pixels that would be translated and calculating the size of those, the length of the translation code and the resultant size in number of bytes, and then do the same thing to calculate the size of the tree structure, and then use the sum of those two to calculate the effective size of the output image. So as you can see, we get about a 16 we shrink the image to about 16% of the original size from the of the original image, which was about 900 kilobytes.
So when optimizing our hardware implementation, we found it to be quite challenging to manage DSP utilization while at the same time pipelining the DCT module due to the large number of multiplications that the matrix multiply functions use in the DCT. However, through careful management of resources, we're able to create a design that, while slightly increases resource utilization, is able to provide around 25x speed up in latency compared to the baseline design. When looking at the actual performance, comparing the software implementations to the deployed FPGA implementations, we can see that the software implementations perform worse than the FPGA implementations. However, this is without the O3 compilation flag. So as you saw on the past slide, the speed up of the optimized FPGA implementation was not too significant compared to the baseline implementation. However, this is in large part due to the host to FPGA communication latency, which was measured to be around 1.5 seconds. So if we actually subtract this latency, we're able to find that the true speed up of our optimized design is around 8 times faster than the baseline design. So now I will do a demonstration showing the JPEG compression accelerator on the FPGA.
So here I've loaded a bitstream of our optimized implementation. And after it runs, you can see we have metrics on the compression data, as well as the accuracy of the design and the execution time. This produces the channel data, which we can send to our MATLAB script to show the decompressed image. So when we run our MATLAB script, we are showing the original image as well as the compressed image. And if I zoom into a section of the image, we can see that the original image looks quite pixelated. However, there is noticeable artifacting on the compressed image, showing that the lossy JPEG compression is indeed functional.
Here's our conclusion. As our demo shown, we successfully developed a functional JPEG compression accelerator which produced a accurate compressed image, and the combination of task level and data level parallelism create an optimal design. We found it pretty challenging to find a middle ground between hardware utilization and speed up, since most of our attempts result in higher latency or lower latency with significant overutilization. Although the host to FPGA communication speed is a major bottleneck for our application, our optimized design still yields 8 times improvement in interface adjusted performance.